Suppose you want to write a Taylor series to approximate natural log of x, and you need it to be quite precise. You need it to be correct to within 1 over 100,000, but not all the time. You could never guarantee that it's that good all the time, but you want to guarantee it's that good at least when I plug in values between 1/2 and 3/2. And I want to know what degree Taylor polynomial I'll need to have. Now this is the kind of question you might ask if you're programming a calculator that only has a certain number of significant digits. There's no point in making the calculator figure out natural log to such an accurate degree that it can't even display the digits. So let's think about the kind of Taylor polynomial we might use. Remember that the natural log of x looks something like this, and it crosses the x-axis at 1. That's really our only good choice for an anchor point, which is also called the center of the Taylor series. We're concerned with values from 1/2 to 3/2. So 1 is right in the middle, and also log of 1 is 0. This is something we can easily calculate with. Now let's remember what our error is going to look like. My actual function minus my approximate, my Taylor polynomial, is going to be equal to basically the next term in the Taylor expansion, except the derivative is going to be at some point that we don't know yet. So it's going to look like 1 over n plus 1 factorial times the n plus first derivative at some point c times x minus a to the power n plus 1. So a few things about this. The first is that if we want it to within a certain tolerance, we don't care if it's too high or too low. So we're really talking about the magnitude of the error. I don't care if it's positive or if it's negative, so we can put in these absolute values. The second thing is that we need to find some reasonable approximation for this. I'm not going to be able to figure out exactly what this is, and in particular, c is some value between x and 1, so I have to start looking at what kind of approximations I can get. So the two things that I'm going to really need to learn to approximate are what's this n plus first derivative, and how can I get an upper bound on this? Now I claim the second one is not that bad. So the x's I'm plugging in are between 1/2 and 3/2. So that means the biggest x minus 1 can be in terms of absolute value is 1/2. So I can already upper bound this. Well, let's be a little smart with these absolute values. This 1 over n plus 1 factorial, that's positive, so I don't need it to be in absolute values. I don't know anything about the derivative, so I should probably keep that in absolute values. And now this x minus 1 to the n plus 1, again, the biggest in absolute values that x minus 1 can be is 1/2. So the biggest this can be is 1/2 to the n plus 1. So now the really big mystery that we still have to solve is what does the derivative look like? Let's do the first couple derivatives of natural log of x until we find a pattern. Its first derivative is 1 over x, which I can write as x to the minus 1. Its second derivative is minus 1, x to the minus 2. Its third derivative is, I bring down that minus 2, so I have minus 1 times minus 2, x to the minus 3. For the fourth derivative, I bring down that minus 3, so it's minus 1, minus 2, minus 3, x to the minus 4, and so on. Let's do one more just to make it really obvious what's going on. So in general, if I'm taking the nth derivative of x, and the pattern starts at the first derivative, right? The 0th derivative is a little bit different. If I'm taking the nth derivative, first let's look at the power of x, because that's the easiest. The power of x is just negative n. The fifth derivative has x to the negative 5, the fourth derivative x to the negative 4, and so on. So I'm going to have an x to the minus n. Now I have this minus 1, minus 2, minus 3, minus 4. This is just a factorial, right? If I ignore the minuses, which I will just for a second. So if we ignore the minuses, it's a factorial, but it's not exactly n factorial, it's 1 less factorial. For example, when I'm taking the 5th derivative, I have 4 factorial. When I'm taking the 4th derivative, I have 3 factorial. The last thing to take care of is these negatives. So I can pull those out as negative 1 to some power, and the power is the same as this factorial, right? It's negative 1 to the n minus 1, because that's the number of negatives I have. One good trick is that whenever you have something that's alternating positive and negative, you can put in a minus 1 to the n or minus 1 to the n plus or minus 1, and that'll give you something that alternates positive, negative every time. So now let's put this back into our error approximation. Remember what our error approximation looked like. We'd gotten it to here, 1 over n plus 1 factorial times the n plus first derivative of something times 1/2 to the n plus 1. I can plug in what I know about the n plus first derivative of c. Now notice when I was figuring out my derivative, I used n. This is n plus 1. So every time I see an n, I'm going to put in an n plus 1. I'm taking the absolute values, so this minus 1 goes away. N minus 1 becomes n plus 1 minus 1, which is just n. And x to the minus n becomes x to the minus n plus 1. Now I'm just going to clean this up a little bit. I'm going to put that n factorial on top. Now I need to bound this. I don't know what, oops, all those x's should have been c's. So I need to bound this. If I don't know what c is, I just know that c is, well, it's somewhere between the center of my Taylor polynomial, my a, which is 1, and x, where x is in somewhere between 1/2 to 1. So let's think about how I can bound this. What I want is an upper bound. I want to say that, well, my error is no worse than this. So if I want to make this whole expression as big as possible, I should make c as small as possible. And the smallest c can be is 1/2. So the largest this whole expression can be is if I plug in c is equal to 1/2. And nicely, that's going to make these things cancel. So what I end up with is n factorial over n plus 1 factorial, but this is n times all the numbers less than n divided by n plus 1 times all the numbers less than n plus 1, and a bunch of those are going to cancel, right? This is 1 times 2 times 3 times n minus 1 times n. And on the bottom, this is 1 times 2 times 3 times n minus 1 times n plus 1. So actually, I'm just left with 1 over n plus 1. What I wanted was my error to be less than 1 over 10,000. So I don't exactly know what my error is, but I know that it's at least less than 1 over n plus 1. So if 1 over n plus 1 is less than 1 over 10,000, then certainly my error is less than 1 over 10,000, because my error is less than 1 over n plus 1, and 1 over n plus 1 is less than 1 over 10,000. So this is the same as saying n plus 1 is greater than or equal to, this was 100,000, I think, 100,000, which means n would have to be greater than or equal to 100,001. So this is definitely something that a computer could figure out. And if you do this work up front, then you can guarantee that whenever you're using this computer program and you're plugging in x's that are between 1/2 and 1, that your error is going to be no worse than 1 over 10,000, or 0.00001. Okay, so I said 10,000 instead of 100,000, about 15 times there. Sorry about that. Now that we have the error, I just want to think real fast, what would this actually look like? So I have this expression here from my nth derivative. That can help me figure out what my Taylor polynomial is actually going to look like. Now remember, this only worked when n was at least 1. So if I think about what my general Taylor polynomial with a equals 1, that means centered at 1, is going to look like, it's going to be like this. So let's look at it term by term. This f of 1, remember f of x is log x. So f of 1 is just going to be 0, so that term's going to go away. And now starting at n equals 1, I start to get my nth derivative looking like this equation here. So I can plug that in. Let's maybe think about what the nth derivative of 1 is going to look like. It's going to be minus 1 to some power times n minus 1 factorial, and that's it, because 1 to the minus n is just 1. So that means our Taylor polynomial is going to be pretty easy. So this first term, okay, this is just 1. The f prime, let's see, this is the term when n is equal to 1. So it's going to be minus 1 to the 0, 1 minus 1 factorial, that's the f prime part, and then x minus 1 to the first power. Now let's look at the second term. We get 1 over 2 factorial. Now my second derivative is going to be minus 1 to the 2 minus 1 times 2 minus 1 factorial. Then I keep that x minus 1 squared. For this third term, my third derivative is going to be minus 1 to the 3 minus 1 times 3 minus 1 factorial, and then I keep the n minus 1 cubed, and so on. And my last term is going to look like 1 over n factorial. The nth derivative is going to be minus 1 to the n minus 1 factorial, and that x minus 1 to the n stays. And the reason I wanted to write it out like this is to see that a lot of stuff cancels, right? This 1 minus 1, 0 factorial, remember that's just 1. This is also just 1. So my first term is x minus 1. For my second term, this minus 1 to the 2 minus 1, that's minus 1, so it's going to be negative. And I have 1 factorial over 2 factorial, which is 1 over 2. For my third term, this is minus 1 squared, so that's just going to be 1. And 2 factorial over 3 factorial, that's just going to be 1 over 3. And in general, in my nth term, I'm going to have it either be positive or negative. See, they're going to be alternating. The first term is positive, the second term is negative, the third term is positive. And then this n minus 1 factorial divided by n factorial is just 1 over n, because everything cancels. Almost everything cancels. So my general form is going to look like, I'm going to alternate positive, negative, positive, negative. It's going to be x minus 1 to the first, x minus 1 to the second, x minus 1 to the third, and so on. And I'm going to divide by whatever term I have. So x minus 1 squared divided by 2, x minus 1 cubed divided by 3. Now I actually want to show you what this looks like. Adding up the 99,999 terms we talked about would be pretty hard for any computer program that you're getting for free. But we can do it to a smaller number of terms. If you're familiar with sum notation, this sum notation on the left just shows you exactly what I showed you in the notes. If you're not, don't worry about it. This is the 1000th degree Taylor polynomial of the form that we were calculating. It's not the 99,000th, but it's the 1000th degree. And you can see at 2 something weird happens, but we're not concerned about 2. We're only concerned about numbers between a half and 3 halves. So let's compare this to natural log. This red line, that's the natural logarithm, and the blue line is our approximation. Now, after 2, they get really bad. But actually less than 2, they look pretty good, even though this wasn't exactly the 99,000th. But we can still zoom in. And we can see that they are indeed different. They do start to diverge, and this looks like this is maybe showing up in the 10,000ths place. Now, one thing to remember when we're getting this accurate is that the computers are also only making an approximation. And since this is some free online thing, it might not be making an approximation up to 100 digits or anything. So if it shows them being extremely close, maybe they're actually not that close, but maybe the computer is using the same approximation that we're using. But the idea is you can see that, okay, it looks pretty close to what a computer would give you for log of x, as long as you're less than 2. And if you want to make that much more accurate, you have to do the calculation we do to really figure out, to really guarantee that your calculation has the error that you want. Now, since the computer is struggling a little, why don't we go down to a much lower order? Why don't we go down to something like a 10th order Taylor polynomial? There's our 10th order Taylor polynomial, and even this isn't so bad. It doesn't get quite as close to 2 as the other ones did, but near 1. It certainly looks pretty good to me.